2 फिलहाल करा रहा हूँ इसके अंदर, जो फ्रेश बैच, इसमें हम चैप्टर नंबर 2 कर रहे हैं। चैप्टर नंबर 2 स्टार्ट किया, तो आज तो आप कंटिन्यू कीजिए। एट द एंड ऑफ द क्लास फिर मैं आपके साथ डिस्कस करूंगा कि बैकअप वगैरह कैसे होगा, किन बैचेस में आना है। आप मरियम की सिस्टर हैं, राइट? ठीक है, एट द एंड ऑफ द क्लास हम डिस्कस करते हैं। So Jumaina, you were not there for the last 2 classes.
Yes, I didn't have the connection.
Okay. So did you watch those lectures on YouTube?
So I couldn't find the lectures. I had searched it before as well after these 2 classes, but then I couldn't find in YouTube.
Couldn't find it on YouTube. Okay, I'm just sharing on the group right now. I'm just sharing.
Okay, sir.
So you have your school today from 11 a.m.
No, today, yeah, 11 a.m. Today from 11 a.m.
Could be just 1 hour class.
But then for me, like 11 o'clock to 12 o'clock, it's biology. But then I don't have bio. So for me, from 12 to 2.
For you, it's 12. And what about Afroza and
They have biology, but then they don't have second period. It's computer.
Okay, so they will be free from 10 to 11 only.
Yeah.
So we have to shift the timings. On Sunday, the timings are it's up to 11. The school is up to 11 only on Sunday.
Yes, up to 11.
So we can have classes from 11:30 onwards, or that would be too hectic.
Okay, sir.
Okay, so let's keep. And your Thursday and Friday are off, right?
Yeah, we don't have on Thursday and Friday.
We don't have any class on Thursday as well as on Friday. So Thursday and Friday. Okay, so we can keep classes on Thursday or on Friday and Sunday. Sunday it would be from 11:30. So 11:30 means. So you're having any recent test?
No, sir, we don't have.
You don't have. So which chapter are you doing in physics?
Took 4th lesson. Started with magnetics.
Doing mathematics. So Giovanna, we have started chapter number 2, that's electric potential. So we have completed up to electric potential due to a dipole. The next topic in electric potential is electric potential energy. The next is electric potential energy. Electric, or you can write this as electrostatic potential energy. So electrostatic potential energy by definition is whenever you have electric forces in your system, say you have a charge, positive charge and a negative charge, these two charges will interact with each other, and due to this interaction, your system will have some net electrical energy, electric potential energy. So the cause of potential energy is, it is due to electric interaction between charges. Electric interaction between charges. Between charges. So electrostatic potential energy is potential energy due to interaction between two charges. And mathematically, you can calculate your potential energy using work done. I'm writing the definition, then we will see how we calculate the potential energy using this definition. So potential energy of system of point charges is work done You don't need even point charges. This definition is valid for any type of charge. System of charges is work done by external force, in carrying charges from infinity to finite separation against the electric field, against the electric field without acceleration. Or in one line, you can simply say that potential energy is simply the work done to make the system. You can simply write this as potential energy is work done to make the system. So the work done to make the system gets stored in the system in the form of potential energy. Just note this definition, then we'll see calculations. Rosa, I have just started this electric potential energy. Just take a screenshot of this definition. So potential energy, I'm just recalling. Potential energy is just due to interaction of two charges. So whenever you have number of charges, they will just interact with each other. And due to interaction, you have potential energy. This potential energy can be calculated through work done in carrying these charges from their infinite separation to finite separation. So if you want to bring those charges from their infinite separation to their respective position, so that work done gets stored in the system in the form of potential energy. So shall I raise it? Aisha, Tuba, Jubena. Aisha. Let's start with the potential energy of a system of 2-point charges. So it's potential energy of system of 2-point charges. So you have a system having 2-point charges. This is the coordinate frame. So the position vector of this point is R1. Let's call this point as A. Over point A, we have a charge plus Q1. Then you have another point B. The position vector of point B is R2. And here the charge is Q2. Now, this charge Q1 and Q2 will interact with each other. Means Q1 and Q2 will exert force over each other. Due to this interaction, the system will have some potential energy. Here, charge Q1 and charge Q2 will exert force over each other. Electric forces, they will repel each other. So, due to this electric force, the system will have some net potential energy. To calculate that potential energy, assume that both of these charges were at infinity. They were at infinity and the separation between the two charges is infinite. If charges are at infinity, that means they will not interact with each other. If they don't interact with each other, that means there is no potential energy of the system. Potential energy is zero. You have to bring these charges from infinity to this point A. You have to calculate work done to make the system. To make the system means you have to bring these charges Q1 and Q2 from their infinite separation to the respective positions. Like you have to calculate work done in carrying Q1 from infinity to point. See, Q2 is at infinity itself. When you are carrying Q1 from infinity to A, there is no other charge. So there won't be any other attraction or repulsion. Means you don't have to do any work done to bring this charge Q1 from infinity to A. So work done, because we always do some work against some force. There is no charge over it. So there's nothing which can attract or repel this Q1. So the work done in carrying Q1 from infinity to point A is 0. So work done in carrying Q1, work done in carrying Q1 from infinity to A is 0. So W1 is 0. That's my first equation. Now, the next is, let's bring this Q2 from infinity to B. When you carry this Q2 from infinity to this point B, then see, there's already this charge Q. This Q1 will try to repel this Q. And due to this repulsion, this Q2 will gain some energy. It will gain some potential energy. So again, when you are carrying this Q2 from infinity to B, then Q1 will repel this Q2. Due to this repulsion, the system will get some net energy. To calculate that energy, you have to use work done. So work done, the next is work done to carry Q2 from infinity to B. So you're supposed to carry Q2 charge from infinity to point B. So the work done will be W2. Work done is charge Q2 multiplied by potential at B minus potential at infinity. Potential at infinity is always 0. Infinity means point where the electrical effect of the charge vanishes. So potential at infinity is 0. But to calculate potential at B, you can use this separation. So it's R1 to R2. This is R1. This is R1. So the potential at point B. So over this point B, potential is due to this Q1 only. So potential at B is 1 over 4 pi epsilon naught. It's charge Q1 divided by separation between A and B. The separation between A and B is R1. So you can substitute the values of V infinity and VB over here. When you substitute these values, work done comes out to be Q2. Potential at B is Q1 over 4 pi epsilon naught R12 minus potential at infinity, which is 0. So the work done in carrying the next charges, it's Q1, it's Q2 by 4 pi epsilon naught R. So this is the work done in carrying this charge Q2 from infinity to B. So the total work done would be total work done W is sum of W1 plus W. So is it clear both the equations W1 as well as W2? Okay. Okay, please note it. W1. Okay. Giovanna, we always do work against some forces. When you are carrying Q2, sorry, when you are carrying Q1, there was nothing in this system. There's no other charge. So there is nothing that can attract or repel Q. So you need not do any work done against anything. There won't be any work done, right? We always do work against any force. When you are carrying Q1, there is no other charge. So there won't be any electric force. No electric force means no work done. Your work done would be zero. But see, when you are carrying this Q2, there is already Q1 here. So Q1 will repel Q2. So against this repulsion, you have to do some work done. And that work done gets stored in the form of potential energy. And that's the work done which we are calculating. Giovanna. Remember, we always do work against a force. If there is no force, that means your work done would be zero. When you are carrying Q1, there is no force, no repulsive, no attractive force. Because Q2 is at infinity. That's why W1 is zero. Tuba, Aisha, Giovanna, shall I raise it? So the total work done is, it's W1 plus W. So the total work done, W1 is 0, W2 is its Q1, Q2 by 4 pi epsilon naught R1. So the total work done is this. This is the total work done, Q1, Q2 over 4 pi epsilon naught R. This is the total work done to make the system. This is total work done to make the system. This total work done will get stored in the system in the form of potential energy. This total work done would be equal to potential energy. This total work done gets stored in the system in the form of potential energy. In the form of potential energy. So potential energy of a system of 2-point charges is simply equal to work done, which is Q1, Q2 over 4 pi epsilon naught R12. This is how we calculate potential energy for the system of 2-point charges. It's Q1, Q2 by 4 pi epsilon naught R. Just note up to here. So it's always equal to work done to make the system. The work done to make the system gets stored in the system in the form of potential energy. Okay. Okay, let's solve some numericals on this concept. The first question. Say you have two charges, a charge of 3 millicoulomb and a charge of minus 2 microcoulomb are placed at a separation of 3 m. So charge of 3 millicoulomb and a charge of minus 2 microcoulomb are placed at a separation of 3 m. You're supposed to calculate the potential energy of the system. So you can calculate potential energy as 1 over 4 pi epsilon naught. It's Q1 multiplied by Q2 over R. So R is the separation between them. Q1 is 3 millicoulomb. So that's 3 into 10 raised to the power minus 3 coulomb. Q2 is minus 2 microcoulomb minus 2 into 10 raised power 6 coulomb. R is 3 mm. That means 3 into 10 raised to the power minus 3. If I substitute all values here, 1 over 4 pi epsilon naught is 9 into 10 raised to the power 9. Q1 is 3 into 10 raised to the power minus 3. Q2 is minus 2 into 10 raised to the power minus 6 divided by R, where R is 3 into 10 raised to the power minus 3. So this will cancel this thing. Potential energy is minus of 18 into 10 raised to the power 3. This is the potential energy of the system. So let's write calculate first part, potential energy. Using this potential energy, you can calculate some more parameters, like this is potential energy, which is minus 18 into 10 raised power 3 joule. You can also calculate work done to make the system. Here, work done to make the system is exactly equal to potential energy, which is minus 18 into, this is work done to make the system, minus 18 into raised to the power 3. Next, using this negative sign of potential energy, you can predict that this system is bounded. If potential energy of your system is negative, negative potential energy means the forces involved are attractive. If involved forces are attractive, that means your potential energy is negative and your system is a bounded system. It's like an atom. In an atom, you have electron and protons. So that electron and proton makes a bounded system. Electron cannot move out of the atom on its own. To move this electron out of the atom, you need some external force. So system of electron and proton, the system of earth and sun, these are bounded systems. So if your potential energy is negative, here potential energy is negative. Potential energy is negative. This negative potential energy shows that your system is bounded. This negative energy shows that system is bounded. If energy were positive, like if this value of energy instead of negative, it comes out to be plus 18 into 10 raised power 3, then the positive energy would be that your system is unbound. Like if you have a positive charge and another positive charge, a proton and another proton. So proton will repel this proton. The system that you will get is a unbounded system. But right now, this is a bounded system. Fourth part. If your system is bounded, then he can ask you to calculate work done to break the system. Work done to break the system. So if work done to make the system is this minus 18 into 10 raised power minus 3. So the work done to break the system would be exactly negative of this. So you can write that work done to break the system is negative of work done to make the system. This is it. So work done to break the system is just negative of the work done to make the system. So you can say that work done to break the system is minus of minus 18 into 10 raised to the power 3. So the work done to break the system is just 18 into 10 raised to the power 3. So this is how we calculate work done to break the system. So is it clear, all four parts? Okay. Okay, then note it. Okay. So shall I raise it? Froza, Shibana, Tuba. Okay, after two charges, if we have a system of endpoint charges, for a system of endpoint charges, if you have a system having endpoint charges, the formula is just if you have endpoint charges, calculate potential energies due to each of the individual charge. Taking pairs, you can, if you have four charges, then you will take pair of two charges each. So the expression of potential energy from endpoint charges comes out to be, it's 1 over 4 pi epsilon naught. It's 1 by 2. This is I equal to 1 to n, j equal to 1 to n. I is not equal to j. It's qi, it's qj over I. This is the formula. You can expand it like this is summation. Summation means you're adding this ith term from 1 to n, and you are also adding this jth term from 1 to n. So the expression of potential energy is this. Potential energy is 1 over 4 pi epsilon naught into half. Instead of I, you can substitute 1. Instead of j, you can substitute 1. So you can write this as, this is q1. And I and j should not be equal. If you take I equal to 1, then your j would be 2. q1, q2 over r1. Next, you can say that your I is 1 now, your j is 3 now. So this will be q1, q3 over r1. Then you can say that your I is 1, but your j is 4, r1. So it keep on continue up to n. This formula is given in NCERT, but in numericals, we will not use this formula. I just have mentioned this formula as it was given in NCERT, but we will not use this in numericals. For numericals, we use other techniques. Just note this formula, then we'll see some numericals on endpoint charges. Don't worry about this formula. Aisha, we are multiplying with this 1 by 2 because when you open this summation, along with Q1, Q2, you will get a term like Q2, Q by R2. So this Q2, Q1 and Q1, Q2 are the same interactions basically. When you open this formula, you get each term twice, each interaction twice. This Q1, Q2 and Q2, Q1 are the same interactions. Similarly, this Q1, Q3 and the next that you can get is Q3, Q1 are the same interactions. So when you open this term, you will get each interaction twice. To make it 1, we multiply it with 1 by 2. Because when you have a charge Q1 and Q2 at a separation, now this is one single interaction. But when you solve this using this formula, you will get two terms. One of Q1, Q2 and another of Q2, Q1. So it's repetition. To make it 1, we just divide it by half. Divide it by 2. Aisha, is it clear? Got it? So shall I raise it? Zubena, Froza, Tuba, Aisha. The next question is, say instead of 2 charges, we have a system of 4 charges. You have a system of 4-point charges. Let's say you have a charge plus E. You have another charge which is plus 2E. You have a charge minus E. And then you have another charge which is minus 2. Each side of the square is A. You're supposed to calculate the potential energy of the system. Calculate potential energy of the system. Potential energy of system. So to calculate potential energy of the system, just count the number of interactions. Like this plus E, by the way, if side is A, then the diagonal would be A root 2, right? The square, if each side of square is A, then the diagonal of the square is A root 2. You're supposed to calculate the potential energy of the system. One method is to use that summation, the formula that we have written in the previous section. But that's very lengthy and complicated thing. Instead of that formula, you can just directly solve this problem by making pairs of 2 charges. See, this E will interact with this 2E. So when E and 2E interact and they are placed at a separation A, so you can simply write that potential energy is 1 over 4 pi epsilon naught. Its charge E multiplied by 2E over separation. Then you can take next interaction. This plus E can interact with this minus E. If plus E interact with this minus E, that's 1 over 4 pi epsilon naught will be repeated. So I'm just taking it to be common. I am taking this 1 over 4 pi epsilon naught to be common. So this is E multiplied by 2E over. Similarly, this E can interact with this minus E. And the potential energy is, let's charge E, take this minus E as negative over it. This plus E can interact with this minus 2E, so that's plus E. That's minus 2E over plus E and minus 2E, the separation is it. So E to E, E minus E, and E is minus 2E, that's the interaction. The next is, you can take other interactions as well, like, so this E with 2E, E with minus E, and E with minus 2E. So all interactions of E are consumed. Next, start with the interaction of 2E. 2E can interact with this E, but we have already considered this interaction. When I say that E and 2E interact with each other, that means interaction of E with 2E or interaction of 2E with E, that's the same thing. We have already counted this interaction, so we will not consider it. Is it clear why we are not considering this interaction of 2E with E? Because interaction of 2E with E and E with 2E are the same interaction. Is it clear? Okay. Next, we can take the interaction of 2E plus minus E. Just check, have we counted this interaction earlier? This 2E plus 2E and minus E. Have we counted this interaction?
No.
Not yet. Huh? So let's take interaction of 2E and minus E. So that's 2E, then minus E over A. Next, we can take interaction of 2E with minus 2. This is again diagonal, it's A root 2. So that is 2E minus of 2E over A. So these are the interactions of 2e. Next, let's count the interactions of minus e. The first interaction of minus e is with plus e. So have we counted this interaction earlier, or we should consider it?
We don't have to consider.
You don't have to consider. Already consider this interaction, like this plus e and minus e. We already considered this interaction. What about minus e and plus 2e? We have already considered or not?
We had considered.
Have considered, like minus e and plus 2e. We have already considered. Last, minus e and minus 2e. The next is this, we have not considered this interaction yet, minus e and minus 2. So it's minus e minus 2e over a. So these are following 6 interactions. So the potential energy is simply, it's 1 over 4 pi epsilon naught. That's 2e square over a. It's minus e square over a root 2. It's minus 2e square over a. Minus 2e square over a. Minus 4e square over a root 2. So this minus e square and this minus 4e square. So when you combine them, that's minus 5e square. It's 1 over 4 pi epsilon naught. See, this 2e square by a will cancel this 2e square by a. You're left with only minus 2e square by a. Minus e square by a root 2 minus 4e square by a root 2. That means minus 5e square over a. The next step, you can take this e square by a as common. So it's 1 over 4 pi epsilon naught. It's e square by a is common. We are left with just minus 2 minus 5 pi. So Giovanna, can you decide whether this system is bounded or unbounded system? Using this expression of potential energy, can you decide whether the system is bounded or unbounded?
Bounded.
It's a bounded system. Because potential energy is negative. If potential energy is negative, that means your system is bounded. It's a bounded system. Okay, just note it down. So shall I raise it?
So, for the second step, there should be one more interaction, right?
Which one? Yes, there one is left, right? This one, huh?
Yes.
Yes, it's plus 2e square by 8, right? So this will cancel this one. So yes. So it would be only minus 5 by 8. Please make this correction. I have missed this term. Plus 2e square by 8 gets cancelled out. So that's yes, minus 5 by 8. So potential energy is negative. That means the system is bounded. Okay, let's erase it. The next topic is, so till now we have done the potential energy of 2-point charges, potential energy of n-point charges. But what if you have field and a point charge? Okay, if you have just a point charge, a charge Q, what is potential energy of the system? Just have one single point charge. What is potential energy? Answers, yes. There is no interaction. The cause of potential energy is interaction. For interaction, you need at least 2 charges or a charge and a field. But if you have just one charge, there is no interpotential energy, no interaction, potential energy is zero. But if you have point charges in electric field, potential energy of a point charge in external field. Potential energy of point charge in external field. So if you have an external electric field, let's say this is the external field. This is the external field. In this external field, we place a point charge Q. So Giovanna, what should be the potential energy of this charge? It should be zero or non-zero. There's single charge, but in field. Potential energy would be zero or non-zero. Giovanna. You have one charge in electric field on a single charge. What should be the potential energy of the system?
The non-zero.
Non-zero. Why?
Because it's an electric field.
Yeah, it's electric field, so this charge will interact with this field, right? So due to that interaction, this charge can have some potential energy. This charge is placed at point A. Over point A, the potential is V1. Due to this charge, this electric field, the potential over this point A is V1. So V1 is potential at A, potential at A due to electric field. It's potential at A due to electric field. That's V1. So to calculate this potential energy, you can start with the same derivation. First, take this charge Q at infinity and calculate work done in carrying this charge Q from infinity to point A. But now to carry this Q, you have to do some work against the electric field. So work done. The approach is same, just calculate work done in carrying your charge from infinity to a point. So work done in carrying charge Q from infinity to A. So work done in carrying charge Q from infinity to A is its charge Q, potential at A minus potential at infinity. So potential at infinity is 0. At A, the potential is V1. So this is the work done in carrying this charge Q from infinity to this point. That's Q V1. And this work done gets stored in the system in the form of potential energy. This work done gets stored in the system in form of potential energy. In form of potential energy. The form of potential energy. So this is potential energy, which is QV1. So this is how we calculate potential energy of a single point charge in electric field. So if you have a point charge in electric field, then potential energy is QV. Just note it down, and they will do if you have 2 point charges in electric field. Expression of potential energy of 2 point charges in electric field. So Froza, you have your school classes from 11 a.m. So let's keep it up to 11 today. Tomorrow I will change the timing. So available at 11:30 tomorrow. Froza and Jubena. So shall I raise it? Yes. Okay. After 1 point charge, then you have potential energy of 2 point charges. Two-point charges. So instead of a single point charge, if we have two charges like a charge Q1 and a charge Q2, charge Q1 is placed at point A, charge Q2 is at point B, potential at A is V1, potential at B is V2, and the separation between Q1 and Q2 are R1. So Duba, can you guess the number of interactions here? Duba, can you guess the number of interactions here? 2. Aisha, can you guess the number of interactions? The number of interactions here? Afroza, the number of interactions in the system? 2. Okay. Shubhana, number of interactions, total number of interactions in this?
4.
4. The correct answer is 3. Total you have 3 interactions. See, this Q1 will interact with the field, first interaction. Q2 will interact with the field, that's second interaction. Q1 will interact with Q2, that's third interaction. Which one is fourth? We have 2 charges in field. So Q1 will interact with field, that's first interaction. Q2 can interact with field, that's second interaction. Q1 and Q2 can interact with each other, that would be the third interaction. So the total number of interactions are 3. Total you have 3 interactions. So the potential energy of the system is, its U is, its Q1, potential is V1. Interaction of charge with field. When charge interact with field, then the potential energy is charge multiplied by potential over that point. Next, Q2 will interact with field and the potential energy is simply Q2V2. Third, Q1 and Q2 will interact with each other. Charge Q1 and Q2 will interact with each other. And the potential energy is simply 1 over 4 pi epsilon naught. It's Q1, it's Q2 over R1. So you have 3 interactions and 3 terms in potential energy. Q1 will interact with field, first interaction. Q2 will interact with field, second interaction. Q1 and Q2 will interact with each other. That's third interaction. So a total 3 terms in potential energy. Is it clear? Not 2. Okay. Just note it down. Shall I raise it? Okay, so you have some electric field. In this electric field, this is some electric field. In this electric field, let's substitute some charges. Like here, let's put a charge Q1. And here, let's put another charge Q. So this is electric field. In this electric field, let's substitute 2 charges. Say the value of Q1 is minus 2 millicoulomb. Here Q2 is minus 3 millicoulomb. The potential over this point is 2 volt. Potential over this point is 5 volt. The separation between the charges is 5 meter, 5 m, or rather take it as 9 m. Calculate potential energy of the system. Calculate potential energy of the system. Calculate potential energy of the system of charges. Calculate the total potential energy of the system. So total you would have 3 terms here. Answers. The straight formula based numerical. You have charges, you have potentials. This is the formula. Na? It's charge Q1 potential at that point plus charge Q2 potential at that point. Then you have 1 over 4 pi epsilon naught. It's Q1 Q2 by R12. So everything is given. Calculate the total potential energy. $360, okay? Okay, 360. Any other answer? Minus 13, okay. Aisha, did you consider the unit conversions? Did you converted this meter, millicoulomb into coulomb, this mm into meter? Because all these equations are in SI unit. Afroza, Tuba. Okay. Try to calculate it up to the last step. And make sure you don't make those silly calculation mistakes. Okay. So the potential energy is Q1. Q1 is minus 2 millicoulomb So it's minus 2 into 10 raised to the power minus 3 multiplied by 2 plus Q2. It's minus 3 into 10 raised to the power minus 3 into V2, which is 5, plus 9 into 10 raised to the power 9. Q1 is minus 2 into 10 raised to the power minus 3. Q2 is minus 3 into 10 raised to the power minus 3 over R12. R12 is 9 mm. It's 9 into 10 raised to the power minus 3. So this 9 will cancel this 9. So potential energy is minus 4 into 10 raised to the power minus 3 minus 15 into 10 raised to the power minus 3. This 10 raised to the power minus 3 will cancel this 10 raised to the power minus 3. So that is 6 raised to the power 6. Into 10 raised to the power 6. Right, so this is minus 0.004 minus 0.015 and this is 6, 3, 6. So the potential energy is 1, 2, 3, 4, 5, 6 minus 0.910019. So it's almost 6, 1, 2, 3, 4, 5, 6. It's almost this. Okay, it was almost same thing. Okay, so Afroza, Fatma, you have joined just now. So I have to stop at 11. You have school classes from 11 a.m. I guess. So Afroza, yes, Giovanna, it's compulsory. Otherwise, you can't add them. Because you can't add them if their powers are different. This is 10 raised power 6 and this is 10 raised power minus 3. You can't just combine them. You can only combine quantities which are having same powers. So 6 and minus 3 will not combine.
So we can combine minus 4 and minus 15, right?
Yes, you can combine minus 4 and minus 15. But you can't combine this whole with this 6 into 10 raised power 6. You can combine quantities having same powers. So it won't work. Okay, so Afroza, Fatma and Jubaina, you can leave. I will update the new timings in the chat room within an hour or something. We have schools classes from 11 a.m. So you can. I'm updating the new fresh class timings in the chat.